so that our on the Wednesday we will focus on the generator transformer and also the what we call that generator transformer, I think the last one, and also the tutorial for your test one. I think your test one will be on 29 April, okay, on Thursday, the next week Thursday. Okay. Okay, so previously, I think just back to this part, I think previously we learned what is the Bucos relay, Bucos protection, and also a simple about the transformer neutral displacement and the use of the what we call that REF, okay, resistive earth fault, and also the displacement of the neutral point, okay, to any displacement of the neutral point. Okay, so I think the transform protection, I think we have done that. Okay, so and this is the explanation about the differential protection scheme. So the relay must operate under normal load condition and for true fault condition. Okay, so during the true fault, so the relay should be stable and it must operate for severe enough for internal fault condition. Okay. And the primary and secondary current of a transformer are normally different from each other and related by their turn ratio. And these currents are displaced in phase from each other by 30 degree. Okay, so the difference between star and delta is a 30 degree. Whether it's a plus or minus depend on the vector group. Okay, if the winding are star delta connected. Okay, and for differential protection, the vector difference of two vector is fed to the operating coil of the relay. Okay, so basically, this means for an external fault of the line, current of the two CT should be equal in magnitude and should be in a phase opposition so that the different current is zero. Okay, so what happened is that I think, okay. For example, if you have a delta at the primary side and the star at the secondary side, okay, and the CT connection for secondary CT connection should be in this form. Okay. Why? Because for the delta, we use a star, and for the star, we use a delta connection here. Why? Because we need to correct back the displacement angle between the star and delta here. Okay, for example, so the delta here already have a 30 degree. For example, it's a positive 30 degree. Okay, so let me change to. Okay, so it's a positive 30 degree. By using this star connection, it's a 0 degree. So the angle here is still 30 degree. Okay, so the displacement is still 30 degree. So the star here is 0 degree. So if we choose a star here, so it will come, it's a 0 degree, and then going to here is 0 degree. So 0 degree, and then they meet with the 30 degree, so it will cause error. Okay, the higher error. Okay, so what they do is they use the delta at the CT connection here. Okay, at the CT connection, so that this delta will minus back the 30. So for example, this 0, they will add more 30. So at the end, this part is 30 degree and this part also 30 degree. Okay, so when they meet 30 degree and 30 degree, it will become 0. Okay, it's just to make sure it become balanced again. Okay. Same goes with the CT ratio. Okay, you can see that the CT ratio at the HV normally, for example, for the step down transformer, so the HV part will be less current and the LV part will be higher current. Okay, so the secondary part, the CT ratio, the how to choose the CT ratio is very crucial. Okay, to make sure that the error at the secondary part is less. Okay. Okay, so this is the example. Okay, bias differential protection is used in the case low fault setting and high operating speed are to be obtained when the following condition exists on the power transformer, which is during the on-load tap changing, during the magnetizing inrush current, and also unmatched CT. Okay, so basically, when we choose the CT, we cannot choose basically previously I mentioned that the CT, they have their own value. For example, you can find that 525/1 or 533/1. So it's very, the value is very what we call that is very simple. It's whether you want 100 or 150, 200, 250. Okay, unless you you bought what we call that, you just buy based on the current. But I think in practical we are not doing that. So basically they are going to have an error here, but to choose the correct CT to choose the CT ratio that will give a minimum error to the system, because at the end of the day, so the operating call here, it requires 20% of the current before it can start operate. Okay, why you need a 20%? Because just to cater for the CT ratio error, okay, between both CT. Okay, so far affect the operation of transformer differential protection relay. Two aspects are of significance. The current flow only in one of two winding of the transformer, and therefore it is as good as an internal fault as far as protection scheme is concerned. Okay, so the wave shape of the inrush current differ from the usual fault current. Okay, and then contain high component of second and also fifth harmonic. Okay, and to take into account the magnetizing inrush current, a high-speed bias differential relay with harmonic restraint feature is used. Okay, so I think previously we learned about the restraint current. So previously we learned about the bias. Sorry, okay, differential. This is the differential, and the top one that we have to is we call that restraint. So we call that is a bias. Okay, so that's why for the transformer we normally say that is a bias differential transformer, because they have a bias and they also have a differential. Okay. Okay, so I think this is just just recall back. Okay, previously the what happened if you have a fault within the winding. Okay, so if you have a fault within the winding, so what happened to the equation here for fault at the fraction x? Okay, from the start point. Okay, so that means, for example, the x, it might be 10% from the start point or 90% of the start point. Okay, so here we can see the phase voltage is Vs over Z3. So what happens if there is a fault? So the IF will equal to X Vs over Z3R. Okay, so basically it's a voltage. To find the current, you have to V over R. Okay, so since it's a V over R, since it's not fully winding, so you have to find the ratio is a X Vs. Okay, and then divide with R. Okay. Okay, and then this, when we change to the equation using this equation, okay, and then the IP and P, I primary, what we call that, this N primary, N is a turn ratio, equal to X square Vs Ns over Z3R. Okay, just change the IF here. Okay, since the IF, based on this equation, you can just put this inside this part. Okay, and then this I primary is equal to IP prime plus IPR. Okay, so basically it's just to change to the one is the per unit, and another one because it's from primary to secondary, so you have to use the IP prime. Okay, base. Okay, and at the end of the day, I think this is the only equation that you use. BSR over Z3 ISR, secondary R. And then back to the original formula here. Okay. So I think, okay, the R is equal to VSR over Z3 ISR. So the R you can change to VSR over Z3 ISR. Okay, R like this. Okay, with the R prime here. And then the NS. Sorry. IP change to IP primes times IPR, and NS, you can change to NS. So let's see the NS. Which one is NS? Excuse me, VSR. Okay, VS equal to VS prime times VSR. So you can just change the VS here to VS prime times VSR. Okay, and then the final one you get is X square VS prime times NS ISR divided with R prime. And for balance, we can okay. I think this for since to make sure the current is balanced, so NP IPR over Z3 equal to NS ISR, and then we rewrite back this in just put the Z3 here at this part. Okay. So basically the IP prime. Okay, I think just you can follow. You can see the how they derive the equation here. Okay, but the final is IP prime is equal to X square VS prime divided with Z3R prime. Okay, and then I think we can also say that X square is equal to IP prime Z3R prime over VS prime. And then for VS prime is equal to 1 per unit, R prime equal to 1 per unit. So the setting is 40%. So, okay, I think this is example. Okay, for the example, relay operate when IP prime more than 0.4 per unit. Okay, or when X more than 3 times 0.4. This is half, that means the, we call that third. Okay, the third. Okay, so this is example if we have the current is 1 per unit and also the resistance is 1 per unit. Okay, and then the setting for our REF is 40%, 0.4. So basically we only cover for 83%. Okay, for internet fault restricted fault protection system is used. Okay, so that's why basically if you have the REF is only cover for 83% of the protected zone. Okay, so I think it's a lot of how they derive this formula. I think you have to look back on this part. Okay, so in order to make sure that the fault at this winding is scattered, so they use what we call that REF, resistive restricted fault protection. Okay, I think we just recall back. I think previously we have mentioned this. Okay. Okay, so this is the example. Okay, using a complete diagram, describe the scheme used to protect delta star transformer towards the main fault. What is the limitation of the scheme used and how to overcome it? Okay, so basically if you have a star and delta transformer, so basically the transformer itself can be the step up voltage or step down voltage. So the first you have to choose the correct CT ratio, and the second is about the displacement of the angle. Okay, the phase displacement. Okay, since it's already 30 degrees, so you have to put both in 30 degree, or you can just use the, for example, this is YD1, you can use YD11, and also you can just maintain this in a star connection. Okay, there is a lot of way, but this is the simplest way how to tackle with the phase displacement. Okay. Okay. Three-phase transformer rated at 33 kV, 6.6 kV is connected in star delta, and the CT protected system at low voltage side has a ratio of 400/5. Determine the CT ratio at the HV side. Okay, so I think this is common question for your test or for your final. Okay, you have a transformer 33 kV, step down 6.6 kV. Okay, so the vector group is the one at the HV is star, at the LV is delta. So how you want to choose the CT ratio. Okay, so this is the solution. So this is the transformer, star and delta. Okay, so low voltage side is star, density is connected Y. Okay, so at the star, so you have to connect it in Y connection, in star connection. This is in delta. Okay, but for the delta connection here, the LV side using a delta connection here, so you have to use the star. Okay, why? Because here you can change to the 30 degree, and the one this you can maintain the 30 degree difference displacement. Okay, so if you use star, that means you maintain the displacement. Okay, if you put the delta, that means you make a displacement to the, for example, this star is 0. When you put this one, so it becomes 30 degree. Okay. If line current is 400 amp at the delta, okay, CT current equal to 5 amp. Okay, line current at a star of the power transformer at the HP side. So it's a 4,000 times 6.6 over 33 kV. 6.6 kV divided with 33 kV. So it's just a ratio here. It's equal to 80 amp. Okay. Okay. So basically, if the LV side is 4,000/5, so we know that the maximum current is 400 because based on the question, they doesn't give the capacity of that transformer. So you can just assume the capacity based on the LV CT ratio. Okay, for example, 400, that means the maximum current that this transformer can carry at LV side is 400 amp. Okay, you just from the 400 amp, you just bring to the primary side. So you have to use the ratio here. So it's 80 amp. Okay, so that based on the 80 amp is so the secondary part surely is 5 amp because the secondary is 5 amp. So the CT ratio at HV side it should be 80 with 5 sub 3. Okay, 5 sub 3. Why sub 3? Because we have a delta here. Okay, we have a delta at the secondary CT. Okay, so this is the CT ratio at HV side. Okay, how to make sure that you have a correct one? Basically, you can use 80 times 3 and 5 times 3. So I think it's just the same ratio. Okay, because the question is just require you the ratio, not the correct HV and LV. Okay. Okay. Next, we have a power transformer that have a rating of 10 MVA, 132 kV, step down 6.6 kV with a delta star connection. Determine the turn at each of the CT so that the current differential scheme can flow 5 amp in the pilot wire. Okay, so determine the turn. So this mean you need to find the turn. This mean the ratio. Okay, for example, you have a this is the solution. The line current you have a 10,000. Okay, this is 10,000 MVA, 10,000 kVA. Okay, that's it. 10 MVA. Divide with 33 times 132 kV. I think if you have K and K here, you can cancel out. This 10,000 K and also 132 K. So you can cancel out K. And then you have 43.73 amp. This is the current at HV side. And the current at LV side, same formula, but the different voltage. Okay, so you just put here 6.6 here. K, kV, and also the top have a K, so you can cancel out the K, and then you get 874.75 amp. Okay, so that means the primary current is 43.73. The secondary current is 874.75. Okay, so this is the connection. CT at delta side is connected Y, and CT at Y side is connected delta. Okay, so I think It's just for displacement. Okay. So the LV side, the CT ratio should be, you have a cert3 here. Okay, why? Because you use a delta. If you use a star, so you can just maintain the 5 here. Okay, so this is the CT ratio. Okay, I think just based on your understanding.
Doktor, ada soalan. Yang tadi tu, yang before ni, yang ni dia bagi cert 3 sebab dia punya delta Y connection
No, this is because it's a 3-phase system.
Oh, okay.
Okay, because the P, what is the for the phase system, P is equal to cert3 IV. Okay, P is equal to cert3 IV. So if you want to find I is equal to S over cert3 V. Okay, or S is equal to cert3 IV. Okay, and then how to find the I is equal to S over cert3 V. Okay, it's come from the S is equal to cert3 IV. Okay. Okay. Next is design the protection of a 3-phase 50 MVA to 130 step down to 34.5 kV power transformer using the available standard CT ratio. The high voltage side is Y connected and the low voltage side connected in delta connected. Specify the CT ratio and sketch the 3-phase wiring diagram of the protection scheme. Determine the current in the transformer and the CT. Specify the rating of the auto transformer if one is needed. Okay, so you are given the capacitor and also the ratio here, and the HV part have a star connection and LV part have a delta connection. Okay, so first you have to find the current at the HV and also the LV. The same formula, you have to use the 40 MVA divide with cert3 and 230 kV. Okay, you're going to find the 1 to 5.5 and also 836.7 here. Okay, so CT at low voltage side connected 1 and the chosen CT ratio is 900/5. Okay, why 900? Because it's near to the 900. It's okay if you want to choose the 850/5. It's still correct. Okay, it's still correct. But maybe it's not practical, but in term academic purpose, it's still correct. Okay, and the secondary current CT ILV is equal to 836.7, and then you have to times with the 5 divide with the CT ratio that you choose. If you choose 850, you have to put here 850. So you get the 4.65. So that means the higher current, if you have a higher load at 836.7, it's not going to reach the 5 amp. The maximum current that it can be reached is only 4.65 amp. Okay, and relay current from the LV side must be balanced with the current that is connected in the delta side. CT at HV side, so okay. Relay current from the LV side must be balanced with the current that is connected in the delta side. CT at HV side. So this requires a secondary current CT which is equal. Okay, so for ICT secondary, so since you have the delta, I think the picture there. Okay, so you have this is the delta, the secondary part. Okay, and then this is the star. Okay, so since you at this side the CT you use the star. Okay, and this part you use a delta. So you have to choose the cert3. Okay, for example. Okay, for LV, so so this require, okay, so ICT for the secondary you need to divide with cert3. Okay, because it's a delta at the primary side. Okay, so it's equal to 2.68 amp. Okay, and to obtain the secondary current CT 2.68 amp, the chosen CT ratio on the HV side is ratio 1 to 5.5 is the current, maximum current, divide with 2.68 is equal to 46.8. And the standard CT ratio available is 250/5. Okay, and if this CT is chosen, the actual secondary CT current is ICT is equal to 1 to 5.5. Okay, so the maximum is only 2.51. Okay, so I think they choose too high in terms of CT ratio in practical. So since I think we should choose 100/5 rather than to use 250. So current in the relay at the HV side is IHV is 4.35. So this is the maximum current that can achieve by the relay. Okay, why we have a 3 here? Okay, because it's just to cater back on the star and delta. Okay, unbalanced current on both sides of the relay. To solve this problem, an auto transformer is used. The ratio of the auto transformer is 4.65 and 4.35. So how you get the 4.65 is based on the here ILB, and 4.35 is based on here at the HV side. So you get the 1.07. Okay, where do you put the 1.07? So basically you are going to put here. Which one is a 1.07? I think it's not catered in this part. Okay, so I think it's not catered in the N auto transformer here. So this is what we call in practical, we call that is a what we call CT factor. Okay, we use the auto transformer, the small transformer at the secondary side, just to correct the value. Okay, so that the error will be very near. So normally we put, I think based on this calculation, it will put at the LV side, not HV side. Okay, so after they put at the HV side, it should be put here. Okay, and the current will become 4.35 amp. Okay, so that this part and this part have the same current, so that the error will be very small. Okay, so don't worry, we will back at this problem. Okay, on Wednesday. Okay, so I think that's all for today. So if you have any question, I think you can save it for next Wednesday. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Thank you, Dr.
Selamat buka puasa, Doktor.
Ya, selamat buka.